RF Man here. Today I want to continue my discussion on how to design, build, and test an RF amplifier. Of course, the RF amplifier we're discussing is the IRF510 push-pull amplifier that we discussed in previous segments. And my discussion today is going to begin with negative feedback. I purposely kept this discussion to the end because I wanted to show the advantages of negative feedback when it comes to harmonic distortion. And during this final part of the video series, we're going to be looking at harmonics, we're going to be looking at intermodulation, distortion, and other areas. So I held this to the last part of the video intentionally so that we could look at some of the advantages on the spectrum analyzer. So what is negative feedback? Well, basically, here's our amplifier, and we have our input signal. Could be input voltage, input current. We have our output signal, and you can see that the amplifier takes the input and amplifies the output. So we have some gain here in voltage or current. Okay, and then what negative feedback does is it takes a portion of the output and it feeds it back to the input. But since the output is 180 degrees out of phase, and you can see that by the waveform here, okay, this is at 90 degrees positive and this is at 90 degrees negative, so we're 180 degrees out of phase from the input and the output. We take a portion of that out of phase signal and we feed it back to the input. So what it does in effect is it subtracts from the input signal. And what does that do for us? It helps us with stability, it helps us with gain, but the trade-off is we lose a little bit of output power. And I'm going to show that when we move on here. So here's our actual circuit with the IRF510, and here's our feedback circuit. So we're using a blocking capacitor and a resistor to take a sample of the output and feed it back into the input, and the blocking capacitor is used to block the DC, and of course the resistor is used to provide the feedback. And this can be in any order. The resistor could be first and then the blocking capacitor second. This is not that critical. But we do need to block the DC that we apply to the drain of the transistor. So what I did here is I made up a table and I used different resistance values to see how much feedback we would get with each of these values. So we already demonstrated without the feedback circuit what the power output was, right? We had 50 watts, okay? And of course, no feedback. This part of the circuit is open. So then what I did was I added a feedback circuit to my design and I tested these different values of resistors. And it's a very tedious calculation to try to determine what the feedback will be mathematically. It's much easier to just establish what the feedback is by modifying your circuit and experimenting with different resistance values. So when I added the 100 ohm resistor in the feedback circuit, okay, the open loop gain without the feedback was 50 watts. The closed loop gain with the resistor dropped to 25 watts. So we have 50% feedback, quite a bit. Then I tested 180 ohms. Again, open loop gain without the resistor in the circuit. Just this is an open loop. Okay, so basically you could just remove this from the schematic. And we had 50 watts open loop and 35 watts closed loop. That gave me a feedback of about 30%. And then finally I tested a 500 ohm resistor. Okay, open loop gain without the resistor in the circuit, again 50 watts, closed loop gain 45 watts. That gave me about 10% feedback. And incidentally, you can do this with wattage, you can do it with decibels, you can do it with voltage. You're going to get the same results. So the question is, what amount of feedback do we use for this type of RF amplifier? Typically, I use about 10%. Okay, and again, it is a trade-off, because the more feedback you have, okay, the less power output you're going to realize, and the advantages may not justify reducing the power to these levels. So 10% feedback gives us pretty good improvement in the overall performance of the amplifier. So if we look at the advantages, what does the negative feedback actually do for us? It improves the stability of the circuit, so we're less likely to have oscillations in the circuit, particularly at different power levels and different input frequencies. So it's much more stable with the feedback. It also flattens the gain. So we know that as we change the frequency, the gain of the amplifier will have a tendency to change. With the feedback circuit, that change is reduced significantly, and the gain becomes much flatter across the band. It also improves linearity and reduces harmonic distortion. Okay, so I'm going to show on the spectrum analyzer improvements in the harmonics. Now, what are the disadvantages? I already said it reduces the gain. As you can see here, we went from 50 watts to 45 watts. So we do have a small reduction in gain, and that results in a reduction in efficiency. So this is a design trade-off. Typically 10% is used for linear amplifiers. So some of you asked if I could take a minute and show my setup here a little closer. So I've got my Striker 10-meter radio here. Of course, we have the board under test. And then I'm using a Daiwa watt meter. This is basically rated for up to 1500 watts. Okay, and you can see that it's used not only to measure the power, but also can measure the SWRs simultaneously. And then I'm using an MFJ 1500 watt dummy load. And later in the video, we'll be looking at the output of the amplifier and looking at the frequency spectrum and seeing how the feedback affects the circuit. Okay, so let me position my camera here so I can get the board in view and the watt meter. I think that's fairly good. Okay, so right now we're running open loop gain. So the feedback resistors are out of the circuit. And if I dead key, you see 50 watts there. So now I'm going to add the feedback resistors. So now we're running closed loop. And you see about 45 watts or so. So as I said, you will get a reduction in the output power, but you will see improvements in linearity and harmonics. So I'm going to take a minute now and set this up on the spectrum analyzer and do the same type of demonstration. All right, so now what we're going to do is take a look at the harmonics with the feedback resistors out and then with the feedback resistors in the circuit. Before I do that, let me just quickly show my setup. I'm taking the output from the board and I'm feeding that into a 30 dB RF sampler, and then I've got my same dummy load here, and I'm taking a 30 dB tap from the sampler and I'm connecting it up here into the spectrum analyzer. So that's the setup. We're going to be sweeping from 1 megahertz to 200 megahertz. That'll allow us to see the 5th and 6th harmonic. And this is set for 10 dB per division. So let's go ahead and apply power and key up the radio, and we'll explain what's going on. So here we see this is our fundamental frequency at 28 megahertz. This is the 2nd harmonic, 3rd harmonic, 4th harmonic, and then we cannot see or barely visible the 5th and 6th harmonic. So the 2nd harmonic is just 2 times the fundamental, right? So 28 times 2, 56. 3rd harmonic is 3 times. 4th harmonic is 4 times. So that's what it looks like without the feedbacks. Now I'm going to add the feedback resistors to the circuit, and let's see if there's any change. Yes, if you look carefully, you could see the 2nd harmonic went up slightly, but the 3rd harmonic went down. So since the 2nd harmonic is already far below the fundamental, okay, more than 30 dB, okay, we did get some additional reduction on the 3rd harmonic, which is not as far below. So overall, we have an improvement in the harmonic distortion. So that's what it looks like. I removed the feedbacks for now, and I'm going to go ahead and show the harmonics now with a 10-meter low-pass filter in line with the circuit, and this is the filter that I will be using here. Alright, so now we're going to take a look at the frequency spectrum and the harmonics with the low-pass filter installed. So let me just quickly show my setup. Here's the RF board. Here's my 10-meter low-pass filter. Goes into my RF sampler and then to the dummy load, and from the tap up to the spectrum analyzer. So let's take a look and see what we get. Remember, we had maybe best case about 30 dB down for the 2nd harmonic, about 26, 27 dB for the 3rd harmonic. So let's see what the effects of the low-pass filter are. So now we're transmitting again, and here's our fundamental frequency. This is the 2nd harmonic. 3rd harmonic's not visible. 4th harmonic's not visible. There's the 5th harmonic. Okay, so the 2nd harmonic, we're 10, 20, 30, 40, 50, 60, greater than 60 dB down, okay, which is excellent. And it looks like also for this harmonic, yeah, better than 60 dB. So the low-pass filter is doing its job and reducing the harmonic distortion. Next, I'm going to set up my system and take a measurement of the IMD, intermodulation distortion. All right, so now we're going to talk about intermodulation distortion and how we do an intermodulation or IMD test. Basically, this test is done on sideband, and it's used to measure the harmonic distortion. So I've got 2 waveforms here. One's on the oscilloscope and one is on the spectrum analyzer, and we'll look at this live on the spectrum analyzer in a few minutes, but let me just give a quick overview. Now here's what a good IMD looks like on the scope, all right? And this is more of a qualitative assessment than a quantitative one. And what we look for here is we want to see a nice symmetrical sine wave as the carrier is being modulated. I don't want to see any flat topping here. I don't want to see any crossover distortion. And this looks very, very clean. That's what a well-modulated signal looks like with a good IMD performance. This is what it looks like on the spectrum analyzer. And basically, we're sweeping this with a center frequency of 28 megahertz. That's our carrier. And then we generate two tones, and we'll show you the setup on that in a minute. And we sweep from 27.99 megahertz to 28.01 megahertz. So that's a bandwidth of 20 kilohertz. 10 kilohertz on this side, 10 kilohertz on that side. And we're able to look at the tones that we generate, and then we're able to look at the harmonics. And we look for around a 30 dB difference would be considered excellent performance for a radio and an amplifier. So that's what we're looking for. So what happens? Okay, I've got my carrier, 28 megahertz. I'm on either lower sideband or upper sideband, and we generate two tones from our audio generator, and these two tones generate harmonics of their own, and you see that's depicted here. Okay, here's my two tones that I'm using, T1 and T2, and each of those tones creates harmonics. So here's the third harmonic, the fifth harmonic, be the seventh harmonic, etc. It's the odd harmonics that are the issue here. And these harmonics are just the sum and differences of the two tones that we're generating. So if we look at the formula, okay, IM3, call that the P3 product, okay, is going to be equal to 2 times the frequency of T2 minus the frequency of T1, and that generates the third harmonic. And then the fifth harmonic would be 3 times T2 minus 2 times T1, and there's our fifth harmonic. Now the important thing here is the difference between the two tones we're generating and these harmonic frequencies. So here's my third, fifth, and seventh harmonic. Also on this side, third, fifth, and seventh harmonic. This is the low side, that's the high side. These are the two tones. Okay, so the two tones we're generating, and we'll see that in a minute with the function generator that I'm using. On the high side, it's 1900 hertz, and on the low side, it's 700 hertz. So there needs to be pretty good separation between the two tones that we're generating, and they can't be harmonics of each other. So for example, if I was using 2 kilohertz for one tone, my second tone couldn't be 1 kilohertz because that's the second harmonic of 2 kilohertz, and they would beat together and affect the actual measurements. So they need to be separated by at least 1 kilohertz, and they can't be harmonic products of each other. Okay, and this is what we're looking for. So here's the setup. Okay, again, I'm using my Striker 10-meter radio. The carrier is 28 megahertz. I'm transmitting on lower sideband. Let me just switch that over. Lower sideband, okay, and we'll be generating a tone. I've got the monitor set so you'll be able to hear the tone as we generate it. And here's our function generator. It's 2 channels, and here's the 2 frequencies that we're generating. We said 1900 and 700, as you can see there, right above my pointer. And the important thing here is they're not harmonics of each other, and they're also in phase. They have to remain in phase, okay? So I have no phase shift between channel 1 and channel 2. And I'm using this interface box that I built. It takes the 2 tones and connects them right into the microphone jack here, okay? And you'll hear the 2 tones as we modulate the carrier. All right, and then we take the output of the radio with the modulated carrier wave, and we're going basically with the same setup. We got an RF sampler, dummy load, and back to the spectrum analyzer. So let's take a look at the tones that we generate, and we'll will explain what's happening. So as I mentioned, looking at the slide, okay, my center frequency, 28 megahertz. Okay, my bandwidth is only 20 kilohertz, right? So I'm sweeping from 2799 to 2801. Okay, so here's my total span, 0.02 megahertz, which is 20 kilohertz. So I have 10 kilohertz on this side and 10 kilohertz on that side of the center frequency. And each box then is 2 kilohertz, right? 2, 4, 6, 8, 10. Same thing here, 2, 4, 6, 8, 10. So we're looking at maybe a width of 4 kilohertz for sideband. We don't want to really go any wider than that. Okay, so I've got it all set up here. I'm going to switch it on. And here we're transmitting at 45 watts. I do have the feedback resistors in there. And you can see, here's my two tones. And let's see what happens when we switch from lower sideband, which is to the left. Now I'm going to switch upper sideband, and you see it move to the right. Okay, I'm going to switch it back on the lower side. So here's my two tones, and here's my harmonic products, 3rd, 5th, 7, 3rd, 5th, and 7. And we expect to be at least 30 dB down. So if we count, we're 10 dB per division, 10, 20, 30, well, about 38 or so. And here, this is a little below the line, so 10, 20, about 30. So excellent performance on the intermodulation distortion. I'll go ahead and turn the monitor off so you don't have to hear those tones. So this is excellent IMD, and you can see how we measure it. Two tones, harmonics, we're looking for at least 30 dB. So we'll switch that off. Okay, so let me just take a few minutes to go through the output board. I just realized I didn't really go into that much detail regarding the board here. So I already talked about the RF chokes. These are material 43. They have 10 turns each. Gives me about 30 microhenries, which meets that minimum 500 ohm requirement. And then I talked about using 2 stacks because of the output power. And this keeps it cooler. And then you see I have some filtering. Here I have 24 volts on this side, 24 volts on that side, and then 1 ground. And then I have some filtering capacitors. The large electrolytic is to filter out the lower frequencies, and the smaller capacitors are used to filter out the higher frequencies. This is a 0.1. You could go 0.01, 0.001. You could add additional filter capacitors. That's a pretty good design practice. I didn't do that here, but that helped clean up the signal. So here, the 24 volts is filtered by these capacitors, and then the RF is choked off so it doesn't feed back into the power supply here. Okay, and then you see that I used some tuning capacitors, okay, on the input side and the output side. And as I explained earlier, I just used a trimmer capacitor and soldered that across here and adjusted it for the lowest SWRs and highest power output. And I did that on this side as well, and you sometimes have to alternate back and forth a little bit. And then I picked fixed values that I used to lower the SWRs, and actually gave me a little bit of improvement on the harmonics and on the IMD as well. So that's a quick overview of the output board. Got this grounded here and grounded here. Grounding is important, but with RF, the important thing is not to have too many ground loops. They basically say single point grounding will give you the best results. All right, so that's an overview of the board. I'm going to now continue. I'm going to show how the board performs and show the output power at different frequencies. All right, so this is the last demonstration for this amplifier. This time I'll be driving it with my function generator. Here we'll be starting at 7 megahertz, and I've got a small 4-watt preamplifier here that we'll use to drive the board. And while I'm increasing the frequency, we'll be able to look at the response on the watt meter. So we'll try to zoom in on that the best we can so you can read the output power. And this is a cross needle meter, so you'll also be able to read the SWRs. So I'm going to start. I mentioned earlier in previous sections that I designed this to operate from 10 megahertz to 30. So we're going to actually start out at 7 megahertz and then work our way up from there. So starting at 7 megahertz here. Okay, and then what I will do is I will just increment the frequency, okay, to 10 and 12 and all the way up, as you see there. I'm not going to move the camera as I increase the frequency, but I think you'll get the idea. Okay, so there's the watt meter, and that's how I'm driving it. And we're going to start with 7 megahertz. So here we go. You can see, yeah, I can drive it about to 70, 80 watts. Okay. I can also angle this so you can see the current as we go up here as well. So again, there's 70 watts or so. Okay, and then we're going to go up to 10 megahertz and drive it again. There we are. Okay, 60, 70 watts. Now I do have a 5 amp limitation on my power supply, so I have to be careful that the overcurrent doesn't trip in. I set that as high as it can go, but that's happened to me as I was testing this and exceeded 5 amps. Okay, so now we'll go to 12 and same test. You see 60, 70, 80 amps, watts there. And we'll go to 14. And again, same thing. You see it swinging up and down. And we'll go to 18. Okay, about 55 or so. And we'll go to 21. Okay. About 50, a little over 50. Then we'll go to 25. And again, you see 50. And then we'll go to 27. And over 50. And then I showed 28 up to 30 with the Striker radio. So that's the demonstration. You can see it performs well from 7 megahertz all the way up to 30. And pretty good efficiency along the whole band. So that's basically what I wanted to demonstrate in this last section. And I do have separate videos now that go into a little bit more detail about how we measure the input impedance with the nano VNA and how we measure the response of the RF chokes, and separate videos on the low pass filter that I used. So what I'll do in this last section, I will attach to the bottom of the video all the hyperlinks of all the other supporting videos that I have out there that might be helpful. So that's it. That's the complete overview here. And I hope that was helpful to many of you. And if you have any questions, just email me or leave a comment. RF Man. Thank you.